In the name of God, hi there. This is Masood. I'm a physics teacher. I'm at your service to explain physics curriculum, grade 11. So far, we've finished the explanation of chapter 1. We got a lot of information about motion and uh, we talked about free fall. We studied kinematic equations with constant acceleration. Right now, we are going to review our information. We are going to recap our information to make sure whether we understand or not, right? So in this lesson, we are going to discuss the questions of chapter 1, review and assess, page 31. Let's get started. Let me read the question number 1. It says, on the graph below, this is the graph, calculate the total distance traveled and the displacement during the recorded time interval. So we look for two things. We look for two information. We look for distance traveled by the moving object. So this is a position time graph of a moving object. We look for distance traveled by this object and also displacement that is traveled by the moving object, right? So how do you calculate the distance? We have a position time graph. Position is plotted on the y-axis and time is marked on the horizontal axis. So at ti is equal to 0, at initial time is equal to 0, so the object actually moves one meters, right? So the first value of let's say position, or in other words, xi is equal to 1 meters, right? How many meters actually are traveled by the moving object? Let's let me show you let me actually determine the final displacement, which is equal to xf, and approximately it points to the what? It points to the 6 meters. So I want you to find the delta x. Delta x here means distance. Because I didn't put any arrow above the symbol, that's why delta x without any arrow above it, this is represent the distance, right? The distance traveled, you have to subtract the first displacement from the last one. So 6 minus 1 becomes 5 meters. Delta x becomes 5 meters without any direction, because distance is not a vector quantity, it's a scalar quantity, or it's a directional quantity, right? About the displacement, uh, the same number, we find the same number for displacement. How do you calculate the displacement? By drawing a straight line from xi to xf, right? Whenever you draw this line from xi to xf, so uh, you get the same result. You get the same value, but here you have to mention the direction, which is positive direction, because the straight line is ascending, the straight line is going up. That's why the direction is positive 5 meters. This is one of the situations in which the distance is equivalent to displacement, and in whenever you want to whenever you to mention the displacement mathematically, you can write the same symbol for displacement delta x, but you have to let's say put an arrow above it, and you have to mention the direction here, which is positive, right? So numerically they are equal, Numerically they are equivalent, but actually you have to mention the direction for displacement. That's it. Right. Question number 2. On a position time graph, actually on a adjacent position time graph, this graph, the same graph. So for question number 2, also we use the same graph. Right. On a position time graph shown adjacent or shown below, what represents the instantaneous velocity? So what thing represents the instantaneous velocity? If you actually go over the previous lessons, I told you that in the case of, for example, curved path, you have to find the slope, and a slope indicates the instantaneous velocity, not average velocity. So in the case of curved path, when we have deviation, when we don't have any straight line, the slope of the actually of the curved path represents the instantaneous velocity. This is the answer. The slope of the line at each point. So instantaneous velocity means a slope, the slope of the line at each point. Right. Question number 3. The position time graph for a bug crawling along a line is shown in figure below. So we have a figure, we have another diagram for the path of bug which is crawling along the line like this. So we have a curved path. There's an inclination or deviation for the bug, and this is the path of the movement of the bug. It says determine whether the velocity is positive, negative, or zero. So we have to analyze velocity, whether it is positive or negative or zero, at each of the times marked on the graph. Right. Let me discuss it with you. This is the graph, and the graph I told you shows us actually the crawling of a bug. This is the path. The answer at t1, at the first time interval, I mean this part. This is t1. At t1, at this position exactly, v is negative. Velocity is negative. Maybe you say, teacher, how do you know velocity is negative here? Because the line actually is descending. The line is getting down. That's why velocity here is actually is negative. At t2, this is t2, right? At this time interval, if you take a look at the curve is getting up. The curve is going up. The curve is ascending. That's why velocity is positive at t2, at t2 especially. And you can say this is t2, right? No problem. So these in this region, actually, in these regions, I can say before the t2 and after the t2 as well. So we have positive velocity. At t3 exactly, v, I'm not actually revealing the answer. I want you to go over it. This is t3, right? At this region especially, whenever you take a look at the curve, you observe that the curve is ascending. It's getting up, right? The line is going up. That's why at t3 velocity is positive, right? At t4, this position, I can say velocity is approximately getting down. It tries to getting down. That's why at t4 exactly velocity is negative. What do you say about t5? At t5, this region especially, whenever you actually focus on the line, you see that the line is horizontal. There is no deviation. There is no deflection. That's why in this position and at that time interval exactly, and at this time interval t5, there's no velocity. Velocity is neither positive nor negative, but it's zero. Right. Question number 4. Use the position time graph in figure above. So we want to use the same graph. Use for question number 4. We use the same graph in previous question. You use the position time graph in figure above to answer the following questions. There are some questions we have to answer them based on the previous graph. Right. A. During which time interval or intervals is the velocity negative? I'm sure you know the answer. You have to mention the time limit because it says time interval. You have to mention 2 times from this one to that one. Right. So we look for what? We look for negative velocity. Let me underline negative for you. So we look for negative velocity. In which time interval exactly we have negative velocity? This is the answer from 0 to t1. From 0 to t1, in this region especially, right? This part. Let me mention it for you. At this position exactly. So from 0 to t1, the velocity is, the curve is descending. What else? We have one more. We have some other time intervals from t1 to t2. This is t1 and this is t2. Also, curve actually from t1 to t2, you observe that the curve is actually going down. From t3 to t4, this is t3 and this one is t4, right? This region exactly. In this region, you see that the from t3 to t4, excuse me, let me, uh, so uh, let me actually mention it for you exactly, right? I'm gonna mention it for you, right? From from t3 to t4, this is t3 and this one is t4. You see that in this position exactly, the line or the curve is going down as well. That's why we have negative velocity as well. And the last one from t4 to t5. From t4 to t5 also we have the same. Also we have the same case. From this region, for this region exactly, this region, you see that the velocity is actually is going down. B, during which time interval or intervals is the velocity positive? So in part B, from the same question, we look for what? We look for positive time intervals. Let me discuss it with you, right? I'm going to discuss the positive. We look for positive time interval, positive velocities actually during some time intervals. The first one, from T1 to T2. From T1 to T2, maybe you see teacher, maybe you say uh, from T1 to T2, we mentioned that the velocity is negative here, and we mentioned the same thing for positive velocity. So I can say from T1 to T2, in some region we have descending case, and after that we have ascending. So I can say it's a mixture of both of positive and negative velocity. If you take a look at this part, especially at the beginning between T1 and T2, at the beginning of the path, we have negative velocity because the line is going down. But at the end of the path between T1 and T2, the line is going up as well. That's why we have positive, actually positive velocity. So maybe for one uh, actually maybe between two successive time interval, we have two uh, directions for velocity. It can be, right? From T2 to T3, from T2 to T3. So we have a positive. Also, we have positive velocity because the line is going up. And the last one from T3 to T4. You see, we mentioned T3 to T4 as negative in previous part. And right now we have the same time interval for positive velocity. And I explained it for you, uh, let's say some minutes ago. From T3 to T4, this part, in some region, velocity is going up, especially at the beginning, right? Especially at the beginning between T1, between T3 and T4. At the beginning, the velocity is increasing. But at the end, right, at the end between T3 and T4, velocities is starting to actually getting down. That's why maybe I told you in some regions, in some time intervals, during some duration, uh, velocity changes its direction, and this is a normal case in physics. Thank you so much, guys, for watching this video, and bye bye.